Okay, I'm trying to start working on section 2.2. Okay, uh, section 2.2 is about uh, series, I think, right? Sequence. Okay, so I'm talking about sequence. Okay. um, so it is like a function whose domain is the set of natural numbers plus 0. Okay, I think usually we set it like a positive integer. Okay. The other name of the set. Okay. So like the positive integer to add or to real number. Okay. So for example, like this one. So this is a function from n to fn. Fn is equal to 1 over n plus 1. So you start with 0. If you have 0, you put 1. 0 equal to 1, give you 1 over 1 equal to 1. Right? And then if you have 1 here, right here, so the fn or the f1 will be 1 over 1 plus 1, so that 1 over 2, right? And so on. Mm, so the function of this one, we call it also as a sequence. So the list of this function is called a sequence. So the sequence from, in general, we represent it something like this. Something like a and in this element of n 0 or positive integer. Like 3, 1, 4, 1, 5, 9, and so on. Okay. And there's another example here. So as you can see that there is a kind of pattern. Okay. For example, like an negative 1 to the n is like alternating sequence here. Yeah, also you can see here that how do we define the term in a sequence. The most common method are either to give an explicit formula for an as a function of n, or through a recurrent equation that allow an when a1 to be calculated from a0 and then a2 to be calculated from a1 and then a3 to be calculated from a2 and so on. So here n is equal as the index of the sequence. So different value of the n correspond to the different terms of the sequence. Okay. So the choice of letters is not important. For example, the m is equal something like that. So this is the same thing as the n element of the positive integer. So the sequence consists of the this. So it is not necessary that our index is run over 0, 1, 2, 3. Instead, we could have indices that run over 1, 2, 3, 4, 4, and so on. So the sequence take value this, and Just another example here. You can see that it start from 0 and then 1 and then 4. So that means it's like A2 with 8. This is A0, A1, A2, A4. So that means you can see that 2 over 2, right? So in general, for an equal to n squared. So find explicit formula for the n term of the sequence. Hmm. So for example 2, you can see like alternating between negative and positive, right? Okay. So you can see the denominator sequence is 1, 2, 3, 4. Right? 1, 2, 3, 4, 5. So just like the first denominator is 1 because 1 over 1 is 1. And so you recognize this sequence as n plus n1, right? Okay. We start from 0. Okay. And putting these two ingredients of the sign of the denominator together, we obtain our explicit formula like this. It start with 0, 0 that means negative 1, 0 plus 1 is 1, so negative 1 over the power of 1 is equal to negative 1. And then down here you have 0 plus 1, so you got 1 here, so that means negative 1 value 1, so you got 1 here, and negative 1. And yeah, you can continue, you can see this formula represent this sequence. And also the sequence do not need to start with n0, however. Right? So we could instead define the sequence by an equal to this. So, but the n is start from 1, not from 0. Okay? So you have to careful that. So this is the recursive definition of the sequence. So, so namely an. Okay, so it's a function of an, right? So it is assumed here the value of an plus 1 depend on the value one step back, right? Namely an. Then the recursion is called the first order recurrent equation. Okay. In the review problem, we will see an example of second order recurrent equation. In this, the same value a plus 1 is depend on the value of a plus a and a minus 1. Okay. So this is called it the second order recurrent equation. So it consists of two step two times step back. Okay. On the values on 1 and 2 times step back. Okay. So to determine the values of the successive members of a sequence given in the recursive form, we need to specify an initial value a0 if we start the sequence of a if this is this start. Yeah, so we need to specify that an initial value is 0 if we start the sequence n equals to 0, or a1 if this if we start the sequence at n1. Okay. The next one is Okay, so you can see here in the notation in this section, the exponential growth of the previous section is given by this. And okay, so yeah, for this one, I think you need to create a spreadsheet to work on it with this kind of problem. Okay. You can call it a recursive sequence. For example, a0 equal to 1 and then a n plus 1 equal to this. Right? So we will use column A for the spreadsheet to store the value of the index n for each term in the sequence, and then column B to store the values of the sequence an. You can see this on the left here. And on the right side, we start from here. So it is start with 0. I mean, it start with n0, n0 equal to 1. Okay. And then n1 is equal to the square root of b2, which is n0 plus 1 plus 1. I mean, so the square root of n0 plus 1 plus 1. Okay. So in this case, the n0 is b2. But if you continue or just simply copy from here down here, give you like the sequence. Okay. And you can see the sequence is like a become constant or close to 3. Okay, so I think this will be related to the, we call it the long-term behavior. Okay. For example, like for the n goes to infinity, what happen to this sequence? So for this sequence, if n goes to infinity, the sequence will be close to 3. Okay. So this is an example. Okay, so you can see, oops. So this is another example. Try to make a moment. So you can see that the limit doesn't exist because it's not. This one you can see the limit also doesn't exist because the limit of the n for n to go to infinity go to infinity. Okay. For this case, you cannot assign any limit because the number is alternating between negative and positive. For this one, so you put it start with n equal to 1, give you a series of this, right? So this is not close to 1, so that's why the limit is equal to 2. So she's talking about the formal definition of limit. So this is the formal definition of limit. So if you have sequence like this, and we call this sequence has a limit a, so we can written as limit n to the infinity a n equal to a. If given any epsilon, there is just a number of n such that a n minus a, absolute value of n minus a less than epsilon. Whenever n whenever n is greater than uh, the capital N. Right? Yeah. So the value of n will typically depend on epsilon. So the smaller epsilon is, the larger n is. So we illustrate the concept of convergence sequence and equal to 50. Okay. So you can see the interval a minus epsilon will be the one that is different. So this is like a the interval of this will be like this, right? So it's for it's from a stripe, it's from a strip of its two epsilon center at A, and then point A n within this. See the strip satisfying the inequality absolute value A n minus A less than epsilon. So for sequence to be convergent, we require that all points A n lie in this strip for all n sufficiently large, namely like larger than some n or some uh, natural number or positive integer. So what this limit, okay, so this is equal to 0, you can use the definition again. Okay. So let's try to find n for a particular choice of epsilon. Okay, say like this, right? So you can notice that this by definition, this will be the absolute value 1 over n minus 0. So, so yeah, minus 0 less than 0 0.03, right? Whenever n greater than n. Right? So by solving this for n positive, we find that we got this, right? Uh, so from here you can see this equal to 3 point, I mean 33.33, right? So for epsilon 0.03, so this is whenever n greater than 33.33. So but to show this is convergent to 0, we need to do the same calculation, right, for any arbitrary epsilon, right? Okay, so you can the definition you can write it like this, right? You can, and then for from here you can see that uh, the an is convergent to 0 if n is greater than 1 over epsilon. So if n equal to epsilon, then whenever, I mean, this can happen whenever n greater than n. Okay, so the formal division of the limit is satisfied. So this is another. So if this is goes to infinity, so this is the definition for the one that is goes to infinity. Okay, so the such that there is a n greater than a whenever equal to 0. And formulate this means that the term in an get larger and larger with the bound as n goes to infinity. Okay. So we also need to discriminate between sequences whose limit are epsilon and epsilon. Okay, so sequence is if given less than precision n less than a correct for, but larger and larger and absolute value is increases. Okay, so this is the law of limits, and I will just try to limit, I mean to try to understand it. Okay, So you can use for solving your problem. Okay. So for a plus an, so the limit equals to the limit of an plus limit of an. So you can do it by yourself. So let me show you how to apply that. Uh, that along. Okay. So for this one, you can split this and into term, right? So if you divide this by n to give you one, and then this one will be one over n. Right? So limit n to infinity, limit one to n to infinity gives you one, but the limit of n for n goes to infinity gives you zero. So one plus zero gives you one. So this limit, the limit for this sequence is equal to one. And for this one is almost the same thing. You need to simplify this, so you need to divide this to give you 4, and then minus 1 over this, right? Okay, so so we can split this too. Okay, so you can, so we usually make this one equal to 4, the limit for this and this equal to 0, so you get this, so the limit for that one will be for this 4. Okay, so this another example. So you can divide, and this is the same limit, this is something, right? Okay, so the next one is it will state the long-term behavior from shear growth for R greater than N, something like this. And this figure indicated that for s equal to 0 if the R is between 0 and yeah. So this one is it. Symptomatic on that. And then and for R1 will go to 0. But for this one, for R greater than 1 is equals to infinity. Yeah, you can draw it. Okay, the next one is the equate the recurrent equations. You can see here we will now discuss how to find such a limit when A is defined recursively. Right? When we define a first order sequence recursively, we express an plus 1 in terms of an. Right? And specify a value of, a value for a0. So calculating a few term, we may be able to guess the limit if it is exists. In some cases, as the next example, we can find a solution of a recurrent equation and then determine the limits if exists using the rule given in the previous section, right? I mean subsection. Mm. So this is an example. So so we can start with an, right, for n equals to 0. Okay. So an, so a1 equal to 1 over 4 is 0 plus 3 over 4, right? So give you, what is the a0? The a0 is 2, right? So give you 1 over 4 times 2, 2 over 4, equal to 5, 4, 5. And you could continue that way, give you, so the limit for this equal to 1, right? And also you can see this kind of a pattern maybe, like 4 to the power of n plus 1 divided by or the power of n. Okay. Yeah, if you want to combine this, it will give you like a yeah, you can combine this too, right? So it could give you um, yeah 5 4 4, right? So this is like this one is like 4 square plus 1. No, not 4 square. Like 4 plus 1. And this one is like 4 square plus 1 divided by 4 square. Uh, so now we can try it as this. Okay, so this another, yeah, so this is about the explanation about how you can get this formula, right? Okay. So if you take the limit, it will give you also 1. So now given the recursive equation, the point A is fixed point, okay, of the recursion relation if A equal to G of A equal to a function of A. So A is fixed point and A0 and A equal to 0. Yeah. A0 equal to A, then A and 1 equal to G of A0. So this equal to GA, G of A and G equal to I mean G equal to G, I mean equal to A, and so on. So if A is 0 equal to A, every subsequent term of the sequence will be equal to A. In many cases, if the limit of the sequence exists, then A must be fixed point of the recursion relation, and the function of G over n must be continuous at A n equal to A. We will discuss the continuous function in the chapter 3, so we can find candidate value for the limit by finding fixed point by solving equal to this. Okay, let's apply this technique to example 13. Okay, the first formula is an plus this, right? So if you have what g of n is equal to 1/4 times an plus 3. So the fixed point for the recursive will satisfy this. Okay. So solving this equation give a equal to 1. If the limit exists, it must be a fixed point. Okay. So in this case, the fixed point will be 1. Yeah, so this is another example. If your limit exists, and an plus 1 is this one, and then a0 this one, so I need to find what is this. Okay, so so you can find, since the problem tell us that the limit exists, we don't have to worry about existence, right? So the problem is that limit is to identify the limit, right? To do this, we need to compute the fixed point. So we can solve A equal to this. Okay, so A will be equal to n equal to 0, so A equal to 3. See, in the question relationship, you have two fixed point. So there are two candidates for limit, right? So a limit an namely equal to 0 or a equal to, we must eliminate one of those point, right? Okay. So notice that the first three terms of the sequence are this and this and this, right? Term in an appear to be increasing, in particular an greater than 2 for all n. So if we can show that to be true, then we can include a0 as a limit. So now if an greater than 2, then this will be greater than 2. Right? So cannot convert to 0 as n to infinity. This rule out one of the possible limit, and we can conclude that the limit an equal to 3. Okay. So this should be greater than 2. So an cannot convert to 0 as n to go to infinity. So this not the limit. So the limit will be the 3. Yeah, you can write this like this. You can see this. The limit is equal to 3, not 0. Okay. So there's another example. Find the fixed point recursion and then test the sequence converts to the fixed point if a is 0 equal to 2. Right? So we can find the fixed point first. So this fixed point will be uh yeah, so you can see here a square equal to 3. So a can be square of 3 or negative square root of 3. Right? So there are two fixed point here. So if a is 0 equal to square root of 3, then a1, a2, and so on is the square root of 3. Okay. And likewise, if using the negative form, we got like this. So if a0 equal to 2, then we find that this equal to this, right? Okay. And you see you continue alternative between 2, and so that the limit of the sequence doesn't exist, right? Okay. Yeah, so this is alternating between this behavior is not sufficient to our choice of initial case. Let's try another initial value. Okay. Negative 3. Then we got this. So successive term now alternating between negative 3 and 1, right? So another between two value, one of which is the initial value, happened with an initial value that is not. So the last example is that has fixed point. I only consider for limit. Okay. So now is using the sigma notation to represent sum of sequences. So like this. Yeah, so you expand this, start with k equal to 1, so give you 2. Oh, that is sum in sigma notation. So number 1 is start from one, right? Not round two. I don't know why. Maybe it is. Oh, okay. So this is the problem. Yeah. So this is another example. Yeah. Yeah. Okay. So for this one is solution is done here. For this one, the solution is done here. And so on. So this is the rule of the sequence using sigma notation. So but the constant value one gives you equal to n. For C and so you can put the C aside of the sigma. So this is like if using distributive property, right? And for last is also equal to like this. Yeah, I think that's about as I don't know whether mini lecture for 2.2. Okay, let's go to the problem.